Hello guys, how are you doing today? I hope you're in great health and thank you for checking by my channel. And a new life update. I'm in college. I'm actually at the dorm today. I will be for 2 semesters or the whole year at the dorm at college. And actually we are trying to cover some courses in digital logics, computer architecture, and calculus seconds. And of course, some fundamental physics, which I will cover too in the algorithm channel. On Instagram too, I'll try to post there too because I'm getting some audiences there. But thank you for this affection that you've given to me, and also this opportunity that for letting me speak or learn day by day, and we learn together. So I'm thankful that the last courses were successful to me and we did it together. I'm pretty sure that some of you have downloaded our app, the Networks app, which is in collaboration with Modex 2020 Modex apps. It was really great collaboration. I really love those guys. But yeah, I'm still working at the channel. I will not let you down. I'll be here for you till the end of college. Hopefully I'll continue after, and we have some results back there too. So I would like to begin with digital logic today and computer architecture because that's what I'm studying for, and that's what I'm hopefully to be best of and be a specialist there. And tomorrow hopefully I will have time to have some conduction there, or some exercises on calculus too. I will record them with my iPhone, which is the highest video quality I can get at the moment. And yeah, thank you for your contribution, for everything you've done to me, and for your views, for your subscribes, and for the comments you've done to me, and likes on the Instagram or Twitter. I don't know, do we have Twitter yet? I don't think so, but thanks for the Instagram though. And yeah, huge thanks to Modex for making this possible and creating apps for me. And together we did a great job there. We have a great team. And as I said, I'm not at the old room, my personal room back in hometown. I'm in college, in the capital city of my country. This dorm is kind of hard to be honest, but never mind. I have a Wi-Fi connection here. It's kind of great, I'd say, but never mind that. If you need more from a personal life or something, which I don't think you care, but whatever, just check out my Instagram and algorithms, of course. But today we're going to talk about digital logic circuit. We're going to begin with logic gates, Boolean algebra, and max specification there. We have some combination circuits, flip-flops, which are really cool, sequential circuits, memory components, and integrated circuits. So let's begin with logic gates. And let's imply that the computer deals with a digital information. For instance, it deals with the information that is represented by binary digits with ones and zeros. But why you choose binary instead of decimal, octal, or hexadecimal? We choose binary if you consider electronic signals, as you can see, with 0, while octal then can go to 0 to 7, which means 8, while with binary we can go 0 to 1 directly. And if you consider the calculation cost, as you can see, 0 0 is 0, 0 1 1, 1 0 1 1 1 is 1 0. You can see in the table there, if you could see some patterns, for example 0 2 4 6 8 10 12 14 16 18, which means by 2, it is incremented by 2. And for example y equals x, is incremented by 2. If you go on a constant line, horizontal, of 0, you can see 0 is incremented by 1, and so on. You get what I mean, right? If you don't, just let me down below the comments and try to explain it. I'm talking about the second table there. We have some basic logic block gates. We have binary digital input signal. As you can see, we have 4 outputs right there. Or we can have many inputs. Sorry, we have 4 inputs in the illustration, but we could have many of inputs there on the gate. Later on, I'll try to give you some logic gates and one output, which can be binary digital output signal. We have some types of basic logic blocks. We have combinational logic block whose output logic value depends on the input logic values. So it means that this block, its output will depend only on the input logic value. It makes sense, of course. We have sequential logic block. The output of logic value depends on the input values and state, which is stored information of the blocks. That's interesting. Functions of gates can be described by the truth table. That's really cool. You can see that later on with A and B and its values. You have the Boolean function and KARNAUGH map, which later on I'll try to describe them step by step, and later on you won't have any problem with it. This is what was I talking about. I will try to explain you later. These are the logic gates. This in the illustration we have combinational gates. We have the name symbol there. If you could check that like in real life, you would highly complete the symbol with DECODER or register, as we call it in my own native language. So sorry for my bad English. You have the function here. You can highly see it and highly understand the function, which is really easy. On the truth table, as I told you, A and B, which are the input, and the other side X, which is output, what give it to us. Let's begin with AND. And as you can see for illustration, the first one has 2 input, that 1 output. It has a sign like how do I say that, like I don't know, is it a real name for that, but this is a straight input and the curvy output, right? That makes sense to you? No problem then. Or do you remember those lights? They're really small lights. Those are mainly on the lighters and some of the cars, RC cars, the old one from Chinese RC cars, the really old, because I'm from 2001 and I remember those, and I don't actually know of these new cars that are way more better and more sophisticated. As you can see from the end, it has 2 inputs and 1 output already. As you can see, the curvy input line has 2 inputs, A and B, and 1 input X. The same from the functions can be called as X is equal 1 plus B, while N can be X times B. You can see I here, or I highly believe this should be the inverse. Okay, I don't know why it's called I there, but never mind. Inverse has 1 input and 1 output. If you could highly see closely with the bubble there, it means the inverse. So the results that you would usually get would be the opposite of it. Crazy, right? Imagine, like, what's wrong with these guys? We have buffer. This is really easy. 1 input, 1 output. We put 0, that would be 0, 1 input, 1 output. X is equal to A. While the inverse is X is equal to A inverse or A prime or A with like a line on the head. But A prime is more cooler and only the cool guys do that. If you use it, the A line there, you're just a nerd. Sorry about that. As you can see, I told you from the inverse, it will be the inverse of the input. If you put 0, it will be 1. If you put 1, it will be 0. If the buffer put 0, it will be 0, 1, and 1. We have NAND. It's a combinations of AND and the inverse of it, as you can see from the bubble, as a head of output. The NAND, we have 2 input, then 1 output. The function of it is x equal a times b. They all are in prime, are in inverse, of course, it's going for the bubble. And let's check the truth table. If the a and b is 0, 0, the output is 1. Why? Usually 0, 0 give us 0, but in this case we have the inverse of it, which means we would have 1. 0, 1 will give us 0 usually, but the inverse will give us 1. 1, 0, of course, as you know, is still 0 because of the AND function truth table, but with the inverse of it, you will get 1, 0 give 1, while 1, 1, which normally will get 1 because it is up and the both functioning usually, but now with the inverse of it, you get 0. We have NOR. This is really cool, I like it. This is the first diode, NOR and exclusive NOR. It's really cool for me because it gives a value of a true engineer and who's working and learn about it or not. As you can see, NOR has 2 input, then 1 output with the bubble, of course, because it is NOR. And the function of it is x equals to a plus b with the OR, but a plus b is on the inverse of it. So it means that what you usually get with NOR or would be the opposite of it. 0, 0 would give us 1, 0, 1 would give us 0, 1, 0, 0, 1, 1, 0. Pretty cool, right? Exclusive OR, this is what I like too. It has 2 input, then 1 output. Here is a sign as a spaceship, but it has like a magnetic field over there. It's not a magnetic field, but I would like to give you some visualization and of course, be more creative. Let's change the function. Don't forget this one, okay? Exclusive OR has the a plus b, but the plus is inside the circle. Don't forget this one. Or if you would like some derivatives, do you remember the product and quotient rule? F prime g plus f prime g times g, f prime times g plus f times g prime. This was the product rule, and you can use this a prime times b plus ab times prime. Yeah, a times b prime, sorry. You can see a, b and products there with the truth table. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. You get it. So we have XNOR, exclusive NOR or equivalence of it. It gives us 2 input and 1 output. As I told you, we have for the exclusive NOR we have the plus in the circle. X is equal a plus b to the circle, all in the inverse. As you can see for the bubble, for the symbol there. Or if you like from a calculus side, if you are really a nerd, just check that. I'm sorry for calling a nerd because I'm a nerd too, and I use that too, don't worry. It's just sarcasm there. I use it 99% of time, because why not? X is equal a times b, no, x a prime times b prime plus a times b. As you can know, a times b we use it for and plus for OR. As you can see here, we have an inverse, OR and AND. Be smart about it and check that out. Let's check the truth table. A, B, and X. 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. Perfect. Of course, you would have Boolean algebra, why not? We have algebra with binary or Boolean. variable or logic operations, Boolean algebra are useful in analysis and synthesis of digital logic circuits. Input-output signals can be represented by Boolean variables, and functional digital logic circuits can be represented by logic operations. For instance, Boolean functions. From a Boolean function, a logic diagram can be constructed using AND, OR, and I. AND, OR, and inverse. Oh my god, this PowerPoint is so lazy. Even lazier than me. Okay, let's check the truth table. The most elementary specification of the function of a digital logic circuit is the truth table. Yeah, no shit. Table describes the output values for all combinations of the input values can be called as mini-terms and can be called the input variables to the power n or different mini-terms. Min-terms. Perfectly. So let's check. We have a few programmers would like it really easy for it. Just pass it for 5 seconds because I'll try to describe what Boolean function is. Because the Boolean functions means only true or false. That's it. Don't listen to crap. Whatever you hear, listen. Just mean true or false. If the function is true, blah blah blah, do that. If the function is false, blah blah blah, do that. Of course, you'll check with conditions, then you'll go the for loop or while loop, whatever function you're using. Boolean function is true or false. True or false. Remember that. Of course, you have a logic diagram. This is for retards. I'm sorry, but I'm a retard too. No, I'm not. Fuck this shit. I'm just trying to give you some visualization regarding the logic diagram. We have x, y, and z, as you can see. Y and z. Y is an inverse. Oh my god, this is really messy, because y has an inverse and is connected with AND. And both of these, x is connected directly with an OR, and y and z is connected together with an AND is connected to OR and gives an output F. Get that right, mate. We have some basic identities of Boolean algebra. X plus 0 is x, plus 1, 1, of course, x plus x gives x. Oh, x plus x prime give us 1, x plus y will give us y plus x plus y plus z give us x plus y plus z. Yeah, no problem. X times y plus z is equal to xy plus xz, x plus y prime, or inverse, whatever you like, nerds, is equal to x prime times y prime, x prime prime, wow, is equal to x, Jesus. Oh, it makes sense because in this case you're kind of multiplying with it, right? So I don't know, if you engineers know more about it, just let me know down below the comments, and I'll try to make a Boolean functions if they are true or false. Okay, we x times 0 of course give us 0, x times 1 x times x, no, see? X times x prime gives us 0, Jesus. X, y is of course yx. X times y z will give us xy times z, x plus y z is give us x plus y plus z, of course. X plus times y prime will give us x prime plus y prime, of course. Okay, this is the Morgan theorem, 15 and 16. Let's check 15 and 16. X plus y of, yeah, no shit. The hell is this theorem? I can do that too. What the hell? I can create a better theorem for like that. Jesus Christ. X plus y prime is equal to x prime plus time y prime. Yeah, Einstein, no problem. And let's check 16. X times y prime is equal to x. Oh, who? Same. What the hell? Who does this shit? Who does this? The usefulness of this table: simplification of Boolean function, derivation of equivalent Boolean functions to obtain logic diagrams utilizing different logic gates. This is ordinarily ANDs, ORs, and inverters, but a certain different form of Boolean function may be convenient to obtain circuits with NANDs or NORs. Oh. applications of De Morgan theorem 15 and 16. You remember that one? X plus y prime is equal to x prime times y prime, and x times y prime is equal to x prime plus y prime. You know, please remember, if you algebra nerds and some of you retards, remember from the algebra with the what's shit called, with ln logarithmetic functions. You can highly check that. Yes, if we have the product there of multiplication, we use plus. If we have there minus, we use multiplication. Yeah, in this case we have plus. We will give you multiplication. If we have multiplication, we give you plus. Yes, no problem. So let's check the usefulness of this table with this allocation Boolean function, blah 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 blah. But a certain different form of Boolean function may be inconvenient to obtain circuits with nans or nors and applications of De Morgan theorem. Oh my god, okay, perfect. Oh shit. As you guys can see, the two inputs are inverse of it. And this is the end. And the end is connected the input of R, and R has the inverse, which means it's the same. Because the inverse of the inverse, where was it shit? The inverse will give us the x. As you can see from 17 of the base identities, x inverse times x inverse times inverse, it means give us x. This is this case. And to nar x prime y prime is equal to x plus y, all in prime. Yes, perfect. And of course, x prime plus y prime give x times y prime inverse and R to NAND. We have some equivalent circuits. There are many different logic diagrams are possible for given function. Let's check the function ABC. This is the AND. Then we use R together with ABC inverse plus A prime C, which is the inverse in the end of with the connected with C. We have AB. Oh my god, this is the end. Then together C plus C, this is R, and we have used the inverse of it. And this is all in R, and we have used the inverse at A times C, which is the end. Let me know down below the comments if this made sense to you or not. Just read more then, or do it all over again, because it's the first time I'm reading it too, and it made sense to me. If not, I'll try to complete it down below the comments. Let me know and I'll try to help you. As you can see from the illustration there, 3 inputs to AND. Those inputs are going to with some inverses there. But all in all, if you can check the function output, the R logic diagram over there, we would have 3 inputs with the R and 1 output. Let's check the second and the third. Okay. So if you understood more about it, the functions are in the first side, and we have them illustrated. But yeah, of course they're messy. But I'm pretty sure you learned it because you are smart guys, you are engineers. Don't worry. I have engineers on my country that don't even know this stuff, but it's better for you to learn so you can be better than them and get higher payment. Let's check the ABC now. Damn, things are really messy though. Like, Jesus Christ. The easiest you could get is the third one. Let's be honest, it's really easy. A times B in the end, plus ORI, A inverse times C, which is the end, and give us the function. Let's check the complement of functions. We have heard the complement of the network scores, do you remember? The 2's complement? Yeah, of course. You have 4, 8, 16, 32, 64, 128, 256, etc. 5, 12. A lot of the stuff. So let's check the complement function. A Boolean function of digital logic circuits is represented by only using logical variables and or and invert operators. The complement of a Boolean function, we have to replace all the variables and sub-expression in the parentheses appear in the function expression with their respective complements. Example A, B to Z, and then the lower letters A, B would give us A invert, B invert, blah blah blah, all inverts. But let's check the function there. P plus Q will give us P plus Q invert. And now we have to replace all the operators with their respective complementary operators, N to R, or to AND, of course. Basically extensification of De Morgan theorem. Do you remember 15 and 16 with the inverse? The genius theorem, or the retard theorem. X1 plus x2 plus blah 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 x to the n give us blah 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 in the inverse. Okay, this is the same with it. Let's see. No, this is the multiplicational. It will give us a product with plus. You see the combination, just like the Morgan theorem. Plus multiplication and multiplication plus, just like the logarithm. Okay, so so this representation has done some simplification there. Truth table, unique to Boolean function, many different expressions exist. And the simplification from Boolean functions is find an equivalent expression that is least expensive to implement. For a simple function, it is possible to obtain a simple expressions for a low-cost implementation, but with complex functions, it is a very difficult task. But what's the reason this presentation doesn't show? Karnaugh map or K-map? Yep. We have heard this K-map, the statistics. K-map, pretty boring, useless. No one gets any shit done with it. K-map is a simple procedure for simplifying Boolean expressions. Because truth table and Boolean function are connected to Karnaugh map. Karnaugh, whatever this guy name is connected by truth table and Boolean function. And this one will give us some simplified Boolean function, which is true or false. So guys, all we did right now was telling to you the truth table Boolean functions, which are connected to K-map, is just a simple procedure at Boolean function, which is Boolean function is true or false. But if you'd like to talk to your professor with it, it means you have to talk some other tales and show him what true and false is, and invent something else just for 2 words. Jesus Christ, where the world has gone right now. Okay, so this is the K-map, the weird map. I don't like this map. I don't know why this map is still alive, but okay. Okay, KARNAUGH map for an input, digital logic circuit, blah 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 blah. It is a rectangle divided into 2 to the power n cells, each cell associated with the mean term. Oh, remember to the end. An output function, value for each input value associated with the mean term, is written in a cell representing the mean term. 1 is cell, 0 cell, each mean term is a 5 decimal number. Whose binary representation is identical to the binary interpretation of the input values of the mean term. Let's check the x and the function. If you want to be cool with it, let's check the input, the output, the dot. 0 give us 1, 1 with zeros. Do you remember this kind of truth table? Or K-map, if you are a retard? This is the inverse, yes, the bubble. Thank you. X 0 1 0 1 duplication cell, K max 0 1 value of f. F of x is the sum of 1 is cell. Jesus Christ. Input x and y in the output f 0 0 0 0 1 1 1 0 1 1 1 1. Oh, this is the end. Do you remember? Yep. Sorry guys. Right now it is 10 o'clock. I've been working all day, going to school. I left my home at 6 a.m. and came home at 9 p.m. It's pretty tiring right now at the moment, but I'm trying to give you some information with it. But don't worry, because you deserve better, guys. Okay, let's check this stuff. Decimal number, x blah blah blah. Just check the function there. X and y will give us the sum, which is 1 and 2. Okay, K-map, pretty boring. Okay, sorry about that. I have to go all in all because I have to learn that too. Why not? X, Y, Z are the input and the function F is the output. Like 0, 0, 0, 0, 0, 1. Oh, as you see here, if you have one bit on, it means the function is still on. It is all 0, give us 0. Let's check the others. Blah blah blah, the same. What do you see here? 1, 0, 1, give us 0. 1, 1, 0, give us 0. 1, 1, 1, give us 0. Which means we only need only 1, 1 there. Do you remember the plus minus rule? We have plus plus give us plus, minus minus plus, but if we have plus minus give us still minus. Yes, if you remember that, you're pretty good now. Or not, please let me know down below in the comments and I'll try to explain you step by step. If you know me by that. Okay, the K map or the boring map. It should be like B map for the IDENTITIES map. 0 0 0 1 1 1 0. This is a binary. Let's check. 2 4 8 16. Okay. 0 1 3 2 4 5 7 6. Perfect. We have the functions x, y, z, which is the sum of 1 to 4. Perfect. And blah blah blah. We have the map specification to adjacent cells. The rule is x times y, which is the end, but this has an inverse prime, or plus x times y end is the same as x that multiplies y plus y, or the inverse is equal to x. Jesus Christ. The binary identifications are different in 1 bit. Min-terms associated with the adjacent cells have one variable complement each other. The cells 1, 0, 1, 1 are adjacent min-terms. For 1, 0, 1, 1 are x times y prime, which give us x equal to 1, y equal to 0. X times y give us x equal to 1, y times equal to 1, can be reduced to f is equal to x from the map, K map. The sheet E map. I said city, sorry for my bad memory. 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1. As I said, we only need 1 bit on, and the whole entire thing will be on. We have the map specification, more than 2 cells. U prime, V prime, Y prime, X prime, blah blah blah, blah blah blah. Nonsense stuff. Blah blah blah. This is the implementation of K-map as a sum of product form. Logic function represented by K-map can be implemented in the form of I and or. A cellular collection of the adjacent one cells can be realized by an AND gate with some inversion of the input variables. Blah blah blah. If we implement the Karnaugh map using 0 cells, the complement of f, for instance f prime, can be obtained. Thus, by complementing f prime using De Morgan's theorem, f can be obtained. If the function of x, y, and z is equal to 0 to 6, so x is 0, 2 is y, z is 6, blah blah blah, implement that stuff, and let's check the visuals. Yeah, inverse equal to x, inverse to zeta, which are the gains of it. So give us the inverse. So let's check the inverse or an AND. The main thing we know is the AND. Here's a function. Oh, we have don't care conditions, as we cared before about K-map then. In some logic circuits, output responses for some input conditions are don't care. Jesus Christ, they really, this call like don't care. What the hell? This condition doesn't care that is 1 to 0, so that's why they call it this name. In the K-map, the don't care conditions are represented by this in the corresponding cells, and the don't care conditions are useful in minimizing the logic function using K-map, which is still useless. Can be considered either 1 or 0, thus increases the chances of emerging cells into the larger cells if we reduce the number of variables in the product terms. Oh my god, what the... Jesus Christ. Not gonna lie, it's the first time for me too, because I still haven't started school yet. I'm just preparing for it, and I'm trying to learn by myself, and this, what the hell am I reading at? The x, y, and z, they're connected with OR, give us a function, we have x and z is inverse, blah blah blah. This is a combinational logic circuit. We have half adder and full adder. We have some other combinational circuits, multiplexer, the encoder, decoder, and parity checker, blah blah blah. 4-to-1 multiplexer, encoder, decoder. Octal binary. Octal is 8 and binary is 2. Oh, really cool, to be honest. This is how it happens. Damn. To be honest, never thought of like that. Jesus Christ. Let's check the D from 1 to 7. The output, we have 3 outputs with the OR gates. It's 0, 1 and 2 for decoder. Oh, why it is octal for something. Let me check. Or 8. Nope. It is 8. But I don't know why the present PowerPoint has done it. Whatever. Did I right? These are the flip-flops. Oh, this is really cool. It means that we have some 500 presentations next. The characteristics of it are two stable states. One is 0, no shit. We have memory capability, operation specified by the characteristic table. 1, 0, 0, 1, two inverses there with the OR gates. You can see how they crossed. This is 0 state because this is 1, 0, 0, 1, we have 0, 1, 1, 0. This is the 1 state. And the main reason of it is because, as I can see here, this is 0, 1, 1, 0, blah blah blah. And in order to be used in the computer circuit, state of the flip-flop should have input terminals and output terminals, so they can be set to certain state. And the state can be read externally. Jesus Christ. We have clocked flip-flops. They are required to be synced to a clock pulse, otherwise the operations of the system may be unpredictable. Okay. Oh, RC latch with preset and clear inputs. Preset clear, CDR, clock. Oh, that's pretty good. It's pretty cool, to be honest. Let's check the D latch. Forbid input values are forced not to occur by using inverter between the inputs. The state transition occurs at the rising edge or falling edge of the clock pulse, latches, and the edge trigger flip-flops. We have D-flop, JK flip-flop, and T flip-flop. JK flip-flop, who's J and K. Oh. Inputs are tied together to make the input. Oh, shish. It toggles whenever there is a pass on T input. Interesting. Clock period determines how fast the digital circuit operates. How can we determine the clock period? And usually the digital circuits are sequential circuits which have some flip-flops. Design procedure. Why has K-map need to be there? It sucks. It is useless. Nobody uses K-map. I've been working a lot of companies in my country and I never heard anybody say we need K-map for this, for that. Like, Jesus Christ, whatever was this guy, I'm pretty sure he had nothing else to do. We have JA is equal to BX here, which means that K is equal to BX, Y. Okay then. JB to X, okay, KB to X, into the clock. X input, B output, design sequential circuits. Okay, we have the counters here. Yeah, finally, Jesus Christ. Now we have the memory, the logic organization here. Words are bytes, or M bytes, n-1, and the RAM here, random access memory. Each word has a unique address. Access to word requires at the same time independent location of the word organization. And data input lines, K address lines, read and write, and data output lines. And these are functions to K words, to the power K words, and bits per word. RAM or read-only memory. It is perform read operation only. Write operation is not possible, of course, because it says read-only. Information stored in RAM is made permanent during production, cannot be changed. Organization, K address input lines, N times N or RAM. M is equal to 2 to the power K, data and data output lines. Information of data output line depend on information that addresses input lines. Combinational logic circuits, blah blah blah. I don't have time for that stuff. You have some types of RAM, PROM, EEPROM. RAM, which is store information function during production. The mask is used in the production process. It is unalterable. It is low cost for large quantity. And quantity production use only the final product. Okay. We have PROM. Not as senior PROM. This is programmable RAM, read-only memory. If you are a nerd like me, who didn't go to PROM, like me, you would like PROM, programmable RAM. Store info electrically using PROM programmer at the user side. This is unalterable too. Higher cost than RAM. Jesus Christ, then. What the fuck do we use that shit? Higher cost than RAM, used in the system development phase, can be used in small quantity system. EEPROM, erasable PROM, store info electrically using PROM programmer at the user side. Stored info is erasable, alterable, using UV light. Oh shit. Oh, shifty. Electrically in some devices and rewritable. Higher cost than PROM, but reusable, used in the system development phase. Not used in system production due to erasability. No shites. Obfuscation by the circuit density, SSI, MSI, LSI, VLSI, TTL, ACL, MOS, MOS. So let's read them. Unit is TTL, is transistor logic. ACL is emitted couple logic, okay. MOS, metal oxide semiconductor, oh cool. CMOS is complementary MOS, which is complementary metal oxide semiconductor. Oh, finally it ended. So thank you guys, this is the first time for me too. And it was pretty cool. I thank you for sticking by. And I'm pretty sure you gave some introduction to that, because why not? We all love learning. I love it too, but why not to do it together? So this was it for today. Please let me know if you have a question. I know it was pretty boring today, but if you did any mistake, please let me know down below in the comments. I'll try to give you a brief description about what happened with it and what we can do, how to fix it. If you have seen the logic of it, I had K-map. I don't like K-map, it's useless, but what can we do? This is school, this is 2020, school doesn't need programmers, they need some guys who knows how to learn fast and forget tomorrow. This is what school needs. But yeah, don't forget the Boolean function. It's not only just a lot of crap, it is really important, of course. Don't take my word for it, because 99% of it is irony. Everything is important, even K-map. And yep, Boolean we talked with logic gates, Boolean algebra. We have talked about math specification, combinational circuits, flip-flop, sequential circuits, memory components. Don't forget the PROM. Of course, not the PROM, senior PROM school stuff, but programmable read-only memory. And this was erasable by UV lights and electrically. It was really cool, to be honest. just to erase things with UV lights. Like, damn. Or the magnets. Where are you from, sir? From 2001? Okay, guys, so thank you for sticking by with me, and I hopefully you understood pretty much of it, and the most part. And let me know down below the comments if you have any question. I'll try to give you every question that I can give to you, and I'll find from Google, because that's what everyone does. Everyone do. And don't forget to check Modex apps on Twitter. And don't forget Modex apps, MODEX APPS. So thank you for sticking by to the end, and have a great time, and hopefully you love it. Goodbye.